Morning, everybody. Sorry I couldn't be here this morning. I forgot to tell you guys yesterday that I was going to be out Tuesday morning. I think I'll be back in the afternoon, but I forgot to tell you guys I wasn't going to be here. So, got a little video for you here. So you keep it brief to introduce you guys to the next topic that we come across when we're dealing with rotational motion. So, today's topic here: what causes changes in rotational motion? How do we get something to spin? How do we get it to stop spinning? These are some questions that we'll talk about here during the course of the presentation. So we're going to start off with a case here, and let's pretend that these two blue squares represent a book. So we talked about a lot earlier in this year that I could take this book, the bottom one, and I could give it a shove and push it, and then across the floor or across the table or something like that. I could give it a shove, and that it would start moving because of the unbalanced force of my hand overcoming static friction. Then it would slide across the table, continuing to move forward because of inertia, but slowing down because of the kinetic friction, and eventually coming to rest in some other place. Force is now balanced. So we talked about that problem a lot, and calculated static friction, calculated kinetic friction, etc., etc., etc. But we could also take that book in another situation, and I could start it spinning, give it a twist, and then eventually friction would cause that book to stop spinning, right? That it would eventually slow down and come to rest from its rotational standpoint. That there would be some angular acceleration that first causes the book to start spinning, right? Just like acceleration first causes the book to start sliding. And then there would be some negative angular acceleration causing the book to stop spinning, caused by friction. And eventually it ends up with a rotational velocity or an angular velocity equal to 0 because it has stopped spinning. So there's some similarities there, but as we've discussed already in this unit, there's definitely some differences about how we define certain things. Excuse me. So, to take that idea and build on it a little bit more, let's talk about the ideas of what this book can do. This is not a picture of a book, it's actually a picture of a hammer, but when we flip that hammer through the air, there's two ways that we can analyze its motion. First, we can look at something that we refer to as translational motion. And that's what we've pretty much talked about all year long. That would be the arc, that's this red arc here, the parabola that is the result of projectile motion, gravity acting on that hammer, causing it to slow down, stop moving vertically up at the top, and begin accelerating back down the bottom again. But now we also have been considering over the past week or so the rotational motion. And the hammer in this picture and the books in the previous slide, you can have both translational and rotational motion at the same time. So far in this unit, we've kind of limited ourselves to just looking at the rotational motion and describing the rotational motion, but we can start having those things at the same time. It can move through space, that's the translational part. Those are all the rules we've talked about so far this year with forces and acceleration and all the things that we've talked about. But then it can also rotate around a point in space. And we've begun to analyze that motion with angular displacement, angular velocity, angular acceleration, the angular kinematic equations. But now we have to take the next step. And if I was on the board, or if I was standing in front of you in the classroom, I would point up to the wall above the whiteboard and say, okay, we've gone here, the first two columns, and then the next thing that we come across are Newton's laws, after gravity, of course. But next thing we come to is Newton's laws. So we have to look at Newton's laws from a rotational standpoint. So the next comic I do is, this is a Far Side comic that I always kind of laugh because when I went to Case, there was a lot of people that I know that would do this. School for the Gifted, and the door clearly says pull, but this guy's pushing. So, you know, I knew a lot of people like this. But I use it to introduce the next topic, that being you opening a door. So, here's a picture. This is a top view of the door, not to scale, but so you got the hinges over here on the left-hand side, and ideally this door is going to open, swing counterclockwise. So from its current position, then up to the top, and then here's a handle over here, a little oversized, but you get the idea. So normally, when we go to open the door, right, you apply, generally not with one finger, but using to illustrate the force, you apply that force to the door on the handle side. And that then causes a rotational motion. The door doesn't actually go anywhere. It doesn't end up in a different place than it was before, but it changes its rotational motion, right? It goes from being closed to being open, and then you can walk through it. And that's all fine and dandy and whatever, okay? But I'm sure we've encountered the situation before where, not so much on a door with a handle, but on the door like with the bar that you push, that you come up to the door and you're not really sure which way the door swings and which side of the door opens, and you end up applying a force really, really close to the side that swings, to the hinges. Now, can you open the door that way? Yeah, you can open the door that way, but you've probably experienced that it's really hard. It's much harder to open that door and get it to open. The closer you are to the hinges, the harder it is to cause that rotational motion that's going to result in the door opening. You can make it happen, but it's a lot harder to do. And then the last option, most of us know not to do this, but we could apply a force to the outside edge of the door and push in towards the hinges. Hopefully you've never tried to open a door this way, and if you have, you probably soon realize that it's not going to help you all that much. It is a force being applied to the door, but in that case there are no changes in rotational motion. The first option, right, going back here, causes a pretty easy change in rotational motion. The door opens quite easily. The angular acceleration is not really hard to produce there. In this case, we can produce angular acceleration. You can cause the door to open, but it's a lot harder. But in this case, no matter how hard you push, you won't cause any change in its rotational motion. So there has to be something about the force that we apply, because hopefully we remember, forces cause change, right? Forces cause acceleration, but it also has to do with the location of where you apply that force. And that's what we're going to get into today. So, like we said, analyzing rotational motion is similar to analyzing translational motion, motion along a line, but we define those terms differently. So we've already defined angular displacement, we've already defined angular velocity, we've already defined angular acceleration. So the next thing that we come across is torque. So as we've just discussed, it's easier to open the door when you push far away from the hinges than it is when you push closer to the hinges. But you can not cause that door to open if you push on the outside edge of the door towards the hinges themselves. And that leads us into the topic that we refer to as torque. Torque, by definition, causes changes in rotational motion, or it causes angular acceleration. Hopefully you're sitting there now going, wait a minute, I know something that causes acceleration. We've talked about that a bunch of times. That's force. Yes, that's true. We generally refer to torque as the rotational equivalent of force because it causes angular acceleration. Is it the same as force? No. There's some other factors that we have to include in there, but it does the same thing as force. It causes an object to change its motion. Not speed up or slow down along a line, but speed up or slow down how quickly it's rotating. Torque depends on two things, as we saw from the demonstration of the forces applied to the door. It depends on the force that we're actually applying, but also depends on where we're applying that force. the distance from the center of rotation. So yeah, it does depend on force, that's true, but force by itself isn't enough to cause torque, isn't enough to cause a change in rotational motion. Where we apply that force also plays a role. So, we calculate torque with the equation tau is equal to F times D times sine of theta. This letter here, this is a Greek letter tau. Let me draw it for you here. Let's see, hopefully this will work, right? I usually draw mine kind of like that, a little curvy at the bottom. Yeah, it looks like a T, but it's a little bit different than T because you don't want to, it represents torque. So tau is equal to F times D times sine of theta. If you've been paying attention, this formula might look familiar or similar to something that we've discussed before. Okay? First, let's go through. That lowercase letter tau, that represents the torque that is going to be applied to that object. The F represents the amount of force that we're actually applying to that object. The D represents something that we call the lever arm. It's a distance. It's a distance from the center of rotation to the point where we are applying the force. So that's the location piece. Like we said, torque depends on two things. The force that you apply, but then also where that force is applied. The lever arm takes care of that where is the force applied. And then theta is the angle between the applied force and the lever arm. And we'll see a picture of that here in just a second. This torque is measured in newtons times meters. Okay, you may have heard torque represented in another unit called foot-pounds, which is the English equivalent of this metric unit, right? Pounds and newtons both represent force. Feet and meters obviously represent distance, but nothing fancy here. We don't call it. It doesn't get its own special name. It's just newtons times meters. So, picture. Here is a wrench, and we're using that wrench to turn this nut right here. So we apply a force to it. There it is. Okay, so there's our force. That's the F part. Generally, we apply this force as far away from the center of rotation as we can. So that increases this D value, and there it is on the picture. Okay, that's what we refer to as the lever arm, the distance from the center of rotation to where we apply that force. And then this angle here, theta, this is the angle between the force and the lever arm. You notice that there's also angle theta here. Obviously those two thetas are not the same thing, but what we find out is that those two thetas, those two angles, will add up to 180 degrees. And if you look at the sine of this bigger angle, the sine of the angle that's greater than 90 degrees, and the sine of this angle that's less than 90 degrees, you'll find out that they give you the same sine value. So we can use either one of those angles. I think this one that I've labeled in purple is a little easier to see. It does result generally in angles that are greater than 90 degrees, but your calculator knows the difference anyway, so it doesn't really matter. So those are the players here, the things that we need in order to cause a change in rotational motion, in order for that nut to begin turning, loosen it up for whatever reason it is. Okay? But what we find out is that not all forces produce torque, and not the same force won't always produce the same amount of torque. So, first, like we discussed, forces that are parallel to the lever arm, or forces that pass through the center of rotation, and we'll see here from the picture that's exactly the same thing, will result in no torque. This is the example of pushing the door along the outside edge. So here's that wrench again. If I apply the force this way, if I push on the edge of the wrench and push it in towards the nut, I have applied a force, but that force is not going to cause a torque. That force passes through the center of rotation. Therefore, the lever arm, which is the distance from the center to where the force is applied, ends up being 0. And we get nothing out of that force. So forces that pass through the center of rotation will not cause torque. And then it really wouldn't be complete unless we had a discussion of component vectors. So only forces or components of forces perpendicular to the lever arm will produce torque. Picture, there's the same picture that we had before. There's the force that we applied, but you can see that it's not perpendicular to the wrench. The wrench from the previous picture, remember, represented the lever arm. So we do this, boom, boom, two components. One that is parallel to the lever arm, and you can see from this picture, yeah, it's pointing away from the middle, but if you talk about the line that it's acting on, that force passes right through the center of rotation, that being the nut that we're trying to turn. So that component is not going to cause any torque. But this component is perpendicular to the lever arm. Therefore, it will cause a rotation. It will cause a torque and cause an a change in the rotational motion or an angular acceleration. This is why the sine theta is built into the formula, because that will ensure that we are getting the correct component that's causing the torque and neglecting the component that doesn't cause torque. So the F is the amount of force that you're applying, the D being the lever arm, the distance from the middle to wherever it is that we're applying the force, and then the theta, sine theta, isolates the perpendicular component, which is the one that causes the torque. So, just kind of reviewing the ideas that we talked about with the door, you have three forces that are applied to this wrench. Which one's going to cause the biggest torque? Hopefully, just kind of knowing what you know, you would say F sub B. Why? Well, if you look at the arrows, it looks like the forces are all the same, but as we have talked about, it's not just the force you apply, it's also where and how you apply that force. F of C passes through the center of rotation, and we already discussed that that force is not going to cause any torque. F of A and F of B are both being applied perpendicularly to the wrench, so the angle is 90 degrees, which, when you plug it into your calculator, sine of 90 is 1, so that helps, but the lever arm is much longer for letter B than it is for letter A, so B would cause the biggest torque. Okay, those are introductory torque concepts, the idea of torque and what it is and how we calculate it. I know I went through it kind of fast. Keep in mind that these notes are available for you online, so you can go and get them and, you know, get all the information that you need and stuff like that. Okay? There was a sheet on the red tray when you walked in this morning called Torque Problems. I would like you to spend the last part of this period working on through some of those things, especially some of the conceptual ones that are at the beginning of the page. Answers to those will be posted online. When we come back, I will see you guys on Thursday for fifth period. I'll see you on Thursday. We'll kind of review those topics at the beginning of class, and then we'll be on to our next lab activity, which deals with torque and hopefully reinforcing some of those concepts. I will see you guys on Thursday. Have a good day, and I'll talk to you later.